Chapter 1, Kinematics. After learning this chapter, you should be able to define displacement, speed and velocity, draw and interpret displacement time graphs, describe laboratory methods for determining speed, use vector addition to add two or more vectors. So we will learn about vectors and scalars, and vectors can be added using the vector addition method. In the O-level class also you would have learned about distance, displacement, speed, velocity, acceleration. Again we will see those and we will go into more detail. Then draw and interpret displacement time graph. So we will first start with displacement time graphs. In the O-level class also you have learned it. The gradient of a displacement time graph is the velocity. And in the next chapter we will learn about velocity time graphs. Okay, and we might also see acceleration time graphs. Then laboratory methods, you will see the instruments that we use to measure speed. Okay, we can use the ticker tape timer and we can use motion sensors. Okay, we will see the details afterwards. And yeah, so now you have an idea of what the topics will be that we will learn in this chapter. Okay, so we have learned the equation for average speed. Average speed is total distance divided by total time. You can write that formula. Average speed is total distance divided by total time. It's not just distance divided by time, it's total distance divided by total time. So it doesn't matter if the object stopped for a certain time, whether it accelerated or whether it moved at a constant speed during the journey. All you need is the total distance and the total time for the journey to calculate the average speed. Now compare this with the constant speed. Now if you have this formula we can use for average speed equal total distance divided by time, and then there is another formula, speed is equal to distance divided by time. Now in that formula we are calculating the constant speed. Okay, so if we have this formula v equals dot, this is the constant speed, where the speed is increasing, the speed is constant, so the distance is increasing at constant time interval, so it travels the same distance in the same time interval. That is what we mean by constant speed. Okay, but if it is average speed, you have to use total distance divided by total time. Okay, then we have something more, that is the instantaneous speed. The instantaneous speed is the speed at a particular moment. For example, let's say you are driving a car. Then you look at the speedometer. The reading on the speedometer is the instantaneous speed. The speed at that moment is called the instantaneous speed. And by the way, whatever is in green bold letters in this book is very important. You have to know the meaning of those words. See, over here you can see average speed is in green bold letters. Instantaneous speed is also in green bold letters, which means you have to know the meanings of those words. It is given here and also it is given in the glossary of your textbook. So if you go to the glossary and if you look for this word, you should be able to find it. You can see over here, this is in the glossary. Average speed is total distance traveled by an object divided by the total time. And if we scroll down, we can find the meaning of the word instantaneous speed. Okay, and here we have the meaning of the word instantaneous. Instantaneous speed, the speed of an object measured over a very short period of time. So that is the speed at that particular moment, and that is the speed that you see on the speedometer when you are driving a car, which gives the speed at that particular moment of the vehicle. Okay, so you have to know the meanings of this word. Whatever that is in green bold letters in your textbook is extremely important. You have to know the meaning, and it is also given in the glossary. Okay, you can see the meaning is given here as well as it is in the glossary. So the best thing you can do is you can see the meaning that is given in that particular chapter and also the meaning in the glossary, put everything together. So you have all the points for the meaning of that word. Okay, then there are different units for speed that we use. The SI unit is meters per second. Okay, meters per second is the SI unit, because meter is a base unit and second is a base unit. You should know the 6 or 7 base units. Okay, meter, second, Kelvin, mole, candela, and so we will see. Okay, so there are 7 base units that you have to know, and all the base units are SI units, but not all the SI units are base units. Okay, Newton is a SI unit, but it is not a base unit. Meter is a base unit, second is a base unit. So if the quantity is given in all base units, that means it can be an SI unit. Okay, so over here this is not in SI units, because centimeter is not a SI unit, meter is an SI unit. Okay, so this is in SI units. Here it is no, so these are not in SI units. The first one is in SI units. Okay, so in physics we will be working with the SI units. Okay, now we are on the next page, page number 2. Okay, the second page of the chapter. Okay, the second page of that chapter, which is page 3 of the book. Make sure you answer all the questions in the brown boxes and check the solutions. The solutions are in the CD of the book, and also if you don't have, you can access it from the drive. It's very important that you answer this question so that you have understood everything in the theory of this chapter. You have to do them and check the solutions. Make sure you get the correct answers. You go through the solutions and make sure you understand all the theory in this chapter. And here we will learn about measuring speed with different instruments. There are different ways that we can measure the speed. The first one is using 2 light gates. As you can see over here in this picture, there is a card attached to the top of this trolley, and what happens is, here we have a light gate. Now also here we have a light gate, and these two are connected to this timer. Now what happens is, when this trolley passes through this light gate, the card blocks the light for a certain period of time. Now when this part of the card passes through the light gate, it blocks the light, and then what happens, it will be blocked for the length of the card, and then after that, after it passes the card, the light will get unblocked. So the timer starts when the light gets blocked over here, and then it stops timing when the light gets unblocked. So in other words, what the timer is doing is timing the time it took for the light to pass this length of the card. Now using the formula speed is equal to distance over time, we can find the speed at the start over here. Similarly, we can find the speed at the stop over here. So we find the initial speed and the final speed. Okay, so we can do that using this. Over here, actually, so sorry, that is actually what is happening here. But over here, what happens is, when it blocks the light, it starts the timer, and then again when it blocks the light here, it stops the timer. So actually it's timing the time to go from here to here. Okay, so the timer will time the time it takes to go from here to here, and you can measure this distance from here to here. Distance divided by time will give you the speed. But what I explained earlier is what is happening here. You can see this timer gets started when it blocks the light, and this timer gets stopped when it unblocks the light, and this will time the time for it to for this card at this point. Okay, so from here to here, that length of the card divided by the time will give you the speed of the trolley over here. Okay, so those are 2 ways. One way is measuring the speed with 2 light gates. The other one is measuring the speed using 1 light gate. And over here, measuring the speed using a ticker tape timer. In the O-level class, you have learned that the time between dots is 0.02 seconds, which means it makes 50 dots in 1 second. So if you want to find the time for 1 dot, it is 1 second divided by 50 dots times 1 dot. So the time between dots is 0.02 seconds. And you can find the speed using the ticker tape also. Okay, so if you see the now this is the start, what happens is the distance between dots is increasing. That means the speed is increasing. Okay, and we can get the length and we can get the time. Now we can measure the length from over here to here, let's say, and we know there are 5 dots, so the time taken is 5 times 1, 2, 3, 4, 5 times 0.02, because from here to here the time is 0.02. So the time between adjacent dots is 0.02. Now we have 1, 2, 3, 4, 5. So the time from here to here is 5 times 0.02 seconds. Then we can measure the distance from here to here. The length of this is the distance the trolley traveled. Distance divided by the time, we can get the average speed, because average speed is total distance divided by total time. Now so far we learned how to measure the speed using 2 light gates, using 1 light gate, using a ticker tape timer, and the fourth method is using a motion sensor. Okay, when you are using a motion sensor, the motion sensor should be placed in the direction of motion of the object. That means it should be placed along the direction of motion. So if the trolley is moving like this or moving away, it should be placed in the path of that object, in the direction of motion of that object. You can't place it, you shouldn't place the motion sensor on the side. Let's say if the trolley is going this way, you should not place the motion sensor on this side or this side. You have to place it in front or behind the trolley in the path that it is moving. Okay, because what happens is this will send waves. You can see it sends waves and receives waves. So what will happen is it sends and receives. Now if it is on this side or this side, what will happen? It will send the wave, but it can't continue sending, because if you place it here, what will happen is it will send the wave. Then once the trolley is over here, then it will send the waves, but the waves will not strike the trolley and come back. So if you place it along the direction of motion, the waves that the motion sensor sends will strike it and come back. Okay, so keep that in mind. You can see here the motion sensor transmits regular pulses of ultrasound at the trolley. It detects the reflected waves and determines the time they took for the trip to the trolley and back. So it hits the trolley and comes back. But if you place it somewhere here, then the waves can't strike the trolley when the trolley is, let's say, somewhere here. If you place the motion sensor somewhere here, but if you place it here, no matter how far it goes, the waves also go, hit it and come back. From this, the computer can deduce the distance to the trolley from the motion sensor. We connect the motion sensor always to a computer or a data logger. Then it can give a graph of distance versus time, speed versus time, acceleration versus time. It can generate a distance time graph. You can determine the speed of the trolley from this graph. Okay, so in an experiment, you have to tell which is the best method to use. You have to pick the method that is the best for that particular experiment. Each of these methods for finding the speed of a trolley has its merits. In choosing a method, you might think about the following points. Does the method give an average value of speed, or can it be used to give the speed of the trolley at different points along its journey? How precisely does the method measure time to the nearest millisecond? How simple and convenient is the method to set up in the lab? Okay, so when you do practicals, you will understand this better, which method to use. Okay, and we mentioned about scalar quantities and vector quantities. A scalar quantity has both a scalar quantity has only a magnitude, no direction, but a vector quantity has both magnitude and direction. For example, velocity. When we say velocity or maybe even displacement, we have to mention the magnitude. Now over here you can see the displacement is given 10 kilometers 30 degrees east of north. This over here is the magnitude 10 kilometers, and the direction is given by this east of north, 30 degrees east of north. So a vector quantity has both magnitude and direction. A scalar quantity has only a magnitude. You have to know the meanings of these. You can see it is again in green bold letters. Okay, and you have to know a list of scalar quantities and a list of vector quantities. Speed, velocity, speed, distance, mass, temperature, volume, those are all scalar quantities. Velocity, acceleration, momentum, moment, magnetic field, electric field strength, those are all vector quantities because they have both a magnitude and a direction. Okay, let's look at this example. Now in this chapter we will learn about distance and displacement. So let's consider this example over here. A person starts at this point A, takes this path, goes to point B, and then continues and goes to point C. This is the path taken by the person. Okay, we need to find the distance traveled. The distance is depending on the path taken. So let's say you are in a car, you take this path, and if you see your meter, the meter in the car, let's say you zero it over here, and then you start going, and then you see this reading on the meter over here. So that will be the distance you traveled. The distance depends on the path. In the beginning, this person traveled from A to B 8 kilometers, and then from B to C, taking this path 7 kilometers. So the distance traveled is 8 plus 7, which is 15 kilometers. Then the displacement is 10 kilometers. The displacement depends on the starting point and the ending point. The shortest distance from the starting point to the ending point is the displacement. Okay, again, the magnitude of displacement is the shortest distance from the starting point to the ending point. In other words, what we can say is it is the length of the straight line joining the starting point and the ending point. Okay, so if you draw a line from A to C, the displacement, the length of that line is 10 kilometers, and this is the magnitude of the displacement. And we also have to mention the direction, because displacement is a vector quantity. You have to mention the direction as well. But this is to indicate that the displacement depends on the starting point and the ending point. It is independent of the path taken, but the distance depends on the path taken. So the distance traveled here is 8 plus 7, which is 15 kilometers, and the displacement is 10 kilometers. Okay, then speed and velocity. You have to know this equation. Velocity is displacement divided by time. Speed is distance divided by time. Velocity is displacement divided by time. Change in displacement divided by time taken. Velocity is a vector quantity. What you can do is draw a table and list the scalar quantities and vector quantities. So in one header you have scalars quantities, and in another header you have the vector quantity. Then you list a number of scalar quantities and a number of vector quantities. Okay, all right. Then we have these different symbols for the different quantities. For distance, we can use D, and the unit is meters. For displacement, some textbooks use S, some textbooks use X. So both X and S are used for displacement. For time, we always use simple T. For velocity and speed, we use simple V. And here are the SI units. Okay, you can see this over here in symbols. The velocity is S is used for displacement. We can also use X for displacement. Velocity is change in displacement over time. This delta here is a Greek letter. If you are not familiar with the letters in the Greek alphabet, there are so many videos that you can watch which explain the Greek alphabet. There are 24 letters in the Greek alphabet. We have both capital letters and simple letters. Why it is important that you know all the letters in the Greek alphabet is in physics, is because in physics you will be using a lot of Greek letters. Okay, the first letter in the Greek alphabet is alpha, second letter is beta, third letter is gamma, and the last letter, the 24th letter, is omega. Okay, we have both capital letters and simple letters. So go through the Greek alphabet. If you Google search it, you can find it, and also there are a lot of videos, like I mentioned before, explaining the Greek alphabet. Okay, this letter delta is capital delta. We used to indicate change. Delta is used to indicate change in physics. So this is the change in displacement. You can see that over here, divided by the time taken for that change in displacement. Okay, so if you want to make t the subject of the equation, or s the subject of the equation, multiply both sides by t, then you will get this. Okay, and if you want to make delta t the subject of the equation, again cross multiply, move the t up there, bring the v down, you will get this. Okay, so if you are good in maths, this is very simple. Okay, here it is again without the delta signs. Okay, first example, make sure you understand all the examples here. A car is traveling at 15 meters per second. How far will it travel in 1 hour? Now, when they give us a question like this, you have to assume the speed is constant. Now, I told you before that equation V equals d over t is used when the speed is constant or when the velocity is constant. Okay, so here we have first we can write the quantities that are given in the question, so you have an idea of which equation you are supposed to use. When you write the quantities like this, you will know which equation has all these quantities, and then you will be able to figure out which equation to use. Okay, the V is equal to 15 meters per second. The time is given in a unit which is not an SI unit, so we can write that and we can convert it to SI units. In 1 hour there is 60 minutes, and in 60 minutes we have in 1 minute we have 60 seconds. So to convert from hours to seconds, you multiply 60 times 60. 1 hour we have 3600 seconds. Okay, so then we can use the formula. Distance is speed times time to get the distance. Okay, 15 is the speed and the time in seconds is 3600 seconds. Okay, so you will get the answer in meters, kilometers. Sorry, you will, if you substitute everything into an equation in SI units, you will get the answer also in SI units. Okay, the SI unit is meters, so you will get the answer in kilometers, meters, and you can convert it to kilometers. The car will travel 54 kilometers in 1 hour. All right, example number 2. The Earth orbits the Sun at a distance of 150 million kilometers. How long does it take light from the Sun to reach the Earth? So the distance from the Sun to the Earth is 150 million kilometers. We know the distance, and also they have given us the speed. So very easy, use the formula. Speed is equal to distance divided by time. You are supposed to find the time. Time is distance divided by speed. We assume the speed is constant, and it is constant. Okay, so the distance is, now here this is in kilometers. You have to convert it to the SI units if you want your answer also in SI units. Kilo is 10 to the power 3. So you can write this as 150 million times 1000 times meter. Okay, the metric prefix K is equal to 1000. There is another video that I have uploaded explaining the metric prefixes like kilo, nano, pico, mega, giga, tera. You can watch that video that explains all these metric prefixes. So here it is 105, it's 1.5 into 10 to the power 11 meters divided by the speed is 3 into 10 to the power 8 meters per second. In the O-level class also you have learned the speed of light. All the electromagnetic waves travel at 3 into 10 to the power 8 meters per second. Then here it is in SI units, here also it is in SI units, therefore you will get the answer also in SI units, 500 seconds. Now you can convert this to minutes. 500 seconds you can convert to minutes, that is you can multiply this by 1 minute over 60 seconds. Okay, so you write here times 1 minute over 60 seconds. Seconds cancel. So it's 500 divided by 60, which is 50 divided by 6. You can use your calculator and then you would get the answer in minutes, 8.3 minutes. So it takes about 8.3 minutes for light to travel from the Sun to the Earth. Okay, you know how to enter it in your calculator. So the scientific calculators you have are much easier to use than the old one. So here we have the exp sign for the old calculator, but here it's x to the power something in the new calculators. Okay, all right. So, and by the way, you have to give it in a sensible unit. Now it doesn't always have to be in meters. If it's a very long distance, if it's like millions of meters, you can write it in SI units. So you should not write all the zeros, or you can also write it with the metric prefixes like megameters, gigameters. Okay, so over here we can write it like this, or we can write it now this has too many zeros, so you shouldn't write it like this with kilometers, or you should not write it like this as in the final answer, because it's a long number. That's why we have scientific notation also called standard form, and also that's why we have the metric prefixes. So you can write it in standard form like this, or you can write it with the metric prefixes. Okay, what is explained here is the consistency of units. For example, if they give the speed in kilometers per hour, and if they give the time in hours, you don't need to convert to meters per second, and you don't need to convert to seconds here. You can directly enter it in the formula, speed is distance over time, then distance is speed times time. Now what will happen is, if the units are consistent, then over here we have kilometers per hour, here we have hours. So per hour and hour gets cancelled out. Okay, so you will get the answer in kilometers directly. So this is to explain that you don't need to convert it. If you see the units, you can write it in such a way so that, like for example over here, the hours and hours cancel out, and you will get the answer in a sensible unit, in this case kilometers. Okay, so make sure you answer all these questions, because it is testing whether you really understood what was explained here. So first is, you have to understand the theory very well. If there is any doubt in anything over here or here in any part of the explanation or examples, make sure it gets clarified, and then you answer these questions. Check the solutions. The solutions are in the CD, it's also in the drive. Okay, then the next topic is displacement time graphs. Displacement versus time graphs. That means displacement is on the y-axis, time is on the x-axis. Always we are supposed to plot the independent variable on the x-axis and the dependent variable on the y-axis. Okay, so here are some results. A toy car moves along a straight track. That means the direction is not changing. Okay, so it's going in a straight line. Its displacement at different times is shown in figure in table 1.3. This data can be used to draw a displacement time graph from which we can deduce the car's velocity. You know, the gradient of a displacement time graph gives you the velocity. You have learned this in the O-level class also. Remember, the gradient of a displacement time graph is the velocity. Okay, so we have this, and on graph paper we can draw a graph and plot the points, and when you do that, you can get something like this. Okay, so if you get a straight line, S versus T, that is S is the symbol for displacement, T is the symbol for time. So if you get a graph of displacement versus time, that is a straight line, the gradient is constant, which means the velocity is constant, because the gradient of a displacement time graph is the velocity. So over here the velocity is constant. Then in the second graph, you can see this gradient is greater than this gradient. That means the velocity for this line is greater than the velocity for this line. Okay, then over here the gradient of this line is 0. That means the velocity is 0. You can see the displacement is remaining the same, only the time is passing. So when the time is passing, the displacement is still the same. So that means it's at the same place. Okay, it's not moving. We say at rest, not moving, stationary. All these words mean the same thing. Stationary, at rest, not moving. Okay, and we use for the word constant, we can use the word uniform. Okay, uniform, not changing. So if you have something like this, the velocity is positive from 0 to time capital T, and then the velocity is negative over here. The gradient is positive here, and then over here the gradient is negative. So from here to here the velocity is positive, and then from here to here onwards the velocity is negative. Okay, so the gradient, okay, what happens over here is the velocity decreases. The way you find the gradient of a curve is by drawing the tangent to the curve at that point. So if you draw a tangent over here, the slope is like this, but if you draw the tangent here, you can see the slope is like that. So with time the gradient of the tangent is decreasing along the curve. If you draw tangents at different points along the curve, you can see that the slope is decreasing. Okay, the slope is decreasing. That means the velocity is decreasing. Something that students confuse is negative velocity with decreasing velocity. Over here the velocity is constant. Here also the velocity is constant. But over here what happens is the velocity is not constant. It's changing and decreasing. The velocity is changing and decreasing. Okay, the velocity is changing and decreasing. Okay, the slope of a displacement time graph tells us how fast an object is moving. So make sure you don't confuse this with this one. Okay, then we have this over here. You can see over here the velocity is constant and then it becomes 0. Sorry, this is, yeah, it becomes 0. So velocity is constant from 0 to 3 seconds and then the velocity becomes 0. So that means it stops. The object stops at this point. At 3 seconds, the object stops. The object starts at an initial displacement of about 1 meter, then moves for 3 seconds at a constant velocity until it reaches a displacement of about 7 meters. Okay, so if you want to find the velocity, you have to use this formula, change in displacement over time. That is 7 minus 1, you can see that over here, divided by the time taken for that change is 3 minus 0. Okay, so you will get 2 meters per second. Now this is actually the gradient what you are finding. You can see change in displacement is the displacement over here minus the displacement over here, and that is the change in displacement. The time taken for that change is 3 minus 0. Okay, so the velocity is change in displacement divided by time taken. So that is 6 divided by 3. So if you are used to finding the gradient of a graph, you may be able to reduce the number of steps in this calculation. Okay, now there are some questions which is related to what you learned just now. Make sure you do all these questions and check the solutions. Okay, make sure you are able to do them all correctly. Okay, so then the next topic is combining displacements. Okay, we have distance traveled is 25 kilometers. In rough terrain, walkers head straight from a prominent landmark. Let's say this is the starting point, goes like this, then like this to the finishing point. The walkers shown in figure 1.12 are crossing difficult ground. Walkers, they navigate from one prominent point to the next, traveling in a series of straight lines. From the map, they can work out the distance that they travel and their displacement from their starting point. Okay, so here is a map. From here to here it's a straight line. We can get the distance, this distance plus this distance plus this, and this will give you the total distance. Okay, so that is 25 kilometers. Lay thread along route on map. Measure the thread against map scale. Okay, then the displacement you can find is from here to here. Like I said, the displacement depends only on the starting point and ending point. It is the shortest distance of the length of the line joining the starting point to the ending point. Okay, so 15 kilometers. Now what you can do is you can use the scale. Maybe 1 kilometer is 1 centimeter on this map. So maybe when you measure it from here to here, it would be 15 centimeters. Now if the scale is 1 kilometer equal to 1 centimeter, 1 kilometer equal to 1 centimeter, then it will be 15 centimeters. Okay, 15 centimeters. If it's 15 centimeters, it will be 15 kilometers from over here to here. Okay, and you also have to specify the direction. So if this direction is north, this direction is east, this will be west, and this will be south. So you can draw a line from here to here and measure the angle. Okay, and I think it is 45 degrees because 15 kilometers north of east. So from the east direction to the north, north of east means the angle is 45 degrees. Okay, then another worked example. A spider runs along two sides of a table. Calculate its final displacement. Okay, so what happens is it starts here, goes like this, from O to A, then from A to B. The spider runs a distance of 2.0 meters, but what is its displacement? Okay, the spider runs a distance of 2 meters, but what is its displacement? You can see how they get 2, that is this plus this. Okay, this one plus this. So 0.8 plus 1.2, that is 2.0 meters. Now, if you want to find the displacement, now this is the starting point, this is the ending point. The shortest distance between the starting point and the ending point is the displacement. So what you can do is you can use Pythagoras theorem and find the length of this side OB. Okay, so that is 0.8 squared plus 1.2 squared whole thing square root. Okay, so 0.8 squared plus 1.2 squared whole thing square root, which is 1.44. Now this is the magnitude of displacement. Displacement is a vector quantity, so you need to get both the magnitude and the direction. Okay, so we got the magnitude, but we need to also get the direction. So what we can do is we can find this angle. Now you know this angle is equal to this angle because they are alternate angles. So if you consider this triangle, this angle theta is opposite over adjacent, which is 0.8 divided by 1.2. 0.8 divided by 1.2. Okay, tan theta is equal to opposite divided by adjacent 0.8, and then you can use your calculator. Arctan or shift tan of this value will give you the angle. Finally, we need to write a statement. The spider's displacement is 1.4 meters at an angle 34 degrees north of east. Because this direction is north, this direction is east. So north of east means this angle. North of the east direction. This angle is what we found over here, 34 degrees. So the spider's displacement is 1.4 meters at an angle 34 degrees north of east. Be careful when you write this. Sometimes students confuse these two. They write east of north. It is not east of north, it is north of east. See, of this east direction, 34 degrees north of the east direction. So that's why we say north of east in short. At an angle 34 degrees north of east. Okay. Okay, next example. An aircraft flies 30 kilometers due east. You can see it's better to indicate it in a diagram like this. 30 kilometers due east and 50 kilometers northeast. Now when they say northeast, the angle is 45 degrees. There was another example earlier. We had here northeast. Northeast means the angle is 45 degrees. Okay, like over here, 45 degrees. An aircraft flies 30 kilometers due east, so from here to here 30 kilometers, and 50 kilometers, so from here to here 50 kilometers northeast, angle is 45 degrees. If it's east, it is moving like in the horizontal direction, the angle is 0. Here the angle is 45 degrees. Calculate the final displacement of the aircraft. So what you need to do is, if you start, okay, you mark this point, mark this point, mark this point. Here to here it is 30, here to here it is 50. Then you can draw a line from here to here, and you have to find the length of that line. Now there are two ways to do this. One is by scale drawing, the other one is by using trigonometry. Okay, so what we can do is we can do a scale drawing like this. Okay, so maybe 1 kilometer is 1 centimeter, like what they have here. So from here to here it will be then 30 centimeters. Okay, from here to here it will be 50 centimeters, right? Because 1 centimeter, if you take as okay, not 1 centimeter, 1 kilometer, 10 centimeters is 1 kilometer, right? Let's look at the scale they used. Okay, over here 1 centimeter is 5 kilometers. So that means if you have 30, then 30 divided by 5 is 6. So from here to here it should be 6 centimeters. Okay, so 1 centimeter is 5 kilometers. Then 50 means 10 centimeters. 50 divided by 5, that will give you in centimeters. Okay, from here to here it should be 5 centimeters. Okay, so what you do is using the scale, 1 centimeter divided by 5 kilometers into 50 kilometers. Then kilometers cancel. 50 divided by 5 is 10. So that's how you get the distance. And the angle you can measure with a protractor. Okay, first you draw this. This is the starting point. 30 kilometers means 6 centimeters using the scale that they have given us. then measure the angle from here 45 degrees from here to here, then it will be 10 centimeters, and then you join this end to this end, and the length of this, so you know the length of this, you know that, then what will happen is in the triangle you already have two sides, then to find the third side you join the two ends here. That will give us, so when you measure it, you will get 14.8 centimeters. Now you have to convert it to kilometers and write it. Okay, so this is in centimeters. 5 centimeters is 1 kilometer. It's better if you write the unit. So over here 14.8 centimeters, here 5 kilometers divided by 1 centimeter. Then centimeter cancels out. You will get the answer in kilometers. Okay. Okay. Then the next one is you have to specify. You have to mention what the angle is, because displacement is a vector quantity which has both magnitude and direction. Okay, so what we can do is use a protractor and measure this. When you use the protractor and measure this, you will get 28 degrees north of east, because from the east direction it's 28 degrees in the north direction. So that's why we say 28 degrees north of east. Again, don't confuse these two. Sometimes students write E of n here. It should be n of e, because from the east direction only we are measuring towards the north direction. In the anti-clockwise direction we are measuring this angle. Okay, so that's why it's 28 degrees north of the east direction. Okay, finally we write a statement. Therefore the aircraft's final displacement is 74 kilometers. Okay, here this is 74 kilometers at 28 degrees north of east. Okay, now this was done using scale drawing. We call this a vector triangle. You can see these three are vectors. We have a vector triangle. I have also uploaded more videos explaining past paper questions like this one. You can watch those two videos to understand these vector questions. Okay, there are past paper questions that I have solved that are arranged by topic. You can check the list of videos there, then see the videos on vectors. You will have a better understanding. There are more examples like this that I have solved there, which are past paper questions. Okay, so here we have a vector triangle. You can see it's a triangle, and so one method is using scale drawing like this. The other method is using trigonometry. Using trigonometry will give us the exact value. When you do scale drawing, you may not measure it very accurately, so you will get an approximation. But if you do trigonometry, you will get the exact answer. Okay, then make sure you do all these questions. Okay, this process of adding two displacements together or two or more of any type of vector is known as vector addition. When two or more vectors are added together, their combined effect is known as the resultant of the vectors. Okay, so here we got the resultant vector. We added this one and this one to get the resultant. Okay, so the topic we did earlier was combining displacements. Now we will combine velocities. Okay, the next topic, combining velocities. Velocity is a vector quantity, and so two velocities can be combined by vector addition in the same way that we have seen for two or more displacements. Imagine that you are attempting to cross a river. You want to swim directly across to the opposite bank. So we have a river and you're trying to swim to the opposite bank, but what happens is the current moves you sideways. The river is flowing, and when the river is flowing, even though you try to swim straight to the other side, you will be directed in a diagonal direction, so you will end up somewhere else. Okay, the current moves you sideways at the same time as you are swimming forwards. Again, under the past paper questions, I have solved a question like this. Okay, now, and also there is an example over here, so we'll go through that to help you understand this better. So what is happening is you are trying to swim from one end of the river to the other end. Okay, so across the river, but the river is flowing like this. So what will happen is, even if you try to swim straight ahead, you will end up somewhere else because the river is flowing perpendicular to the direction you are swimming. The outcome is that you will end up on the opposite bank but downstream of your intended landing point. In effect, you have two velocities. The velocity due to your swimming, which is directed straight across the river. The velocity due to the current, which is directed downstream at right angles, see, perpendicular to your swimming velocity. These combine to give a resultant or net velocity which will be diagonally downstream. In order to swim directly across the river, you have to aim upstream. Then your resultant velocity would be directly across the river. Okay. An aircraft is flying due north with a velocity of 200 meters per second. A side wind of velocity 50 meters per second is blowing due east. Okay, so what happens is the aircraft is flying due north. Now it's trying to fly this way at 200 meters per second, but when it's trying to fly this way, the wind is blowing to the right at 50 meters per second. So what will happen is the aeroplane will not go like this. It tries to fly this way, the wind is blowing this way, so eventually it will end up somewhere there. Is that clear? No. It's trying to go this way, but the wind is blowing this way, so it will end up moving in that direction. Same thing with the example we mentioned earlier about the boy swimming. So let's say if there's a river here, the river is flowing this way to the right, and you are trying to swim like this straight ahead to the other side. But what will happen is, because the river is flowing this way from the left to the right and you are trying to swim this way, you will again also end up there. Okay, and if you want to swim from here to here, and if the river is flowing this way, what you will have to do is you will have to swim in this direction. You will have to swim in this direction, then only you will end up somewhere there. Okay. So there are questions like this in the past papers. Make sure you really understand this example. Okay, so what happens is blowing due east. What is the aircraft's resultant velocity? Give magnitude and direction. So you can draw a diagram like this. It's trying to go this way, the wind is blowing this way, eventually it will end up somewhere there. This is called a vector diagram. Okay, so the resultant will give you the resultant velocity. 200 this way, 50 this way. You can draw the triangle, and using Pythagoras theorem you can find the resultant, magnitude of the resultant. You have a right angle triangle here, because these two are at 90 degrees to each other. The angle here is then 90 degrees. So what you will get is v squared is equal to 200 squared plus 50 squared, and then take the square root, you will get 206 meters per second. This is the magnitude of velocity. Now you also have to find the direction. So you can find this angle using tan. Tan is opposite over adjacent. 50 divided by 200, you get 0.25. So the angle is 14 degrees. Okay, so use shift tan in your calculator, arc tan of this value. Make sure your calculator is in degree mode. If you have it in radian mode, you will get your angle in radians. We want the angle in degrees. Okay, so if you want the angle in degrees, your calculator has to be in degree mode. Make sure your calculator is in the correct mode when you are doing these calculations. So the aircraft's resultant velocity is 206 meters per second at 14 degrees east of north. 14 degrees east of north. Okay, you can see here, this is the north direction. East of the north direction, this angle 14 degrees. Okay, so earlier we had north of east, where it was the other angle, but here we have what? East of north, 14 degrees, capital E of capital N, capital E of capital N. Okay, so 14 degrees east, this is east of the northern direction. Alright, so there are similar questions over here. Make sure you do them. Check the solutions at the back of the book. We have come to the end of the chapter. The summary: displacement is the distance traveled in a particular direction. Always make sure you go through the summary, because it summarizes all the important points in the chapter. Displacement is the distance traveled in a particular direction. Velocity is defined by the word equation. Velocity is change in displacement over time. The gradient of a displacement time graph is equal to velocity. Distance and speed are scalar quantities. A scalar quantity has only a magnitude. Now I told you have to know the meaning of scalar quantity and also the meaning of vector quantity, and you have to know examples of vector quantities and scalar quantities. Displacement and velocity are vector quantities. A vector quantity has both magnitude and direction. Vector quantities can be combined by vector addition to find their resultant. Now over here, the last two examples we did were vector additions. Velocity vector this way, another velocity vector this way, and then we got the resultant velocity of this aircraft due to these two velocities. So that was a vector addition that we did. So the vector quantities can be combined by vector addition to find their resultant. And there are more examples on this. Like I said, where I have solved past paper questions, you can watch those videos about vector additions. Okay, now one more thing. Alright, over here we have the base quantities and the base units. Mass, time, length, electric current. I think I missed this one earlier when I was explaining. The electric current is a base quantity and the base unit is ampere. Okay, so here are the 7 base units: kilogram, second, meter, ampere, Kelvin, mole and candela. I don't think this is in your syllabus, but all the others are there. And here are a list of vector quantities and scalar quantities. We learned earlier a scalar quantity has only magnitude. A vector quantity has both magnitude and direction. Scalar quantities, examples: length, area, volume, speed, mass, density, and distance. Okay, distance is also a scalar. Pressure, temperature, energy, entropy. For chemistry you would learn entropy. Work, power. Then vector quantity examples: displacement, velocity, acceleration, momentum, force, lift, drag. Now these are all types of forces. So all the forces are vector quantities. Lift, drag, weight, thrust, those are all different types of forces. Alright, so that's the end of the lesson.